what we're going to deal with now is nucleophilic addition of amines. These again are very important reactions in biology and enzymology, and how substrates are bound to and then released from enzymes in stronger ways than simply hydrogen bonding. So what we're going to do in this reaction is we're going to convert our nucleophile in the addition to carbonyls from an alcohol to so we need some hydrogens on the amine. So we'll start this with imine formation. Now, biologists have a different name for imine. Biochemists have a different name for imine. They're called Schiff's bases. So if you remember the term Schiff's bases, your biology, biochemistry, and other professors will be very happy with you when they teach you about biomolecules and biochemistry and enzyme catalysis and so forth. These are going to be prevalent there. So first, what are they and what do they look like and how do we make them? So the general reaction here is our quintessential carbonyl. Okay, I'm just going to say it can be an aldehyde or a ketone. Okay, we react that with a primary amine. Okay, again, catalytic H+. Okay, we would use probably a little drop or two of H2SO4. There are solid organic acids like tosic acid that are highly useful for this, but you only want catalytic amount. If you put too much, of course, the amine is much more basic than the alcohol was, and so if you put too much catalyst, the reaction slows down because you protonate it and make ammonium. You have no proton or no lone pairs left to act as nucleophiles. So we have two hydrogens here. So we make we replace the oxygen double bond with the nitrogen carbon double bond, and we make water. So the two protons came from the amine and the oxygen came from the carbonyl. And this is a reversible reaction. Now, when I put up the acetal in the previous section in the discussion, did you realize that I also taught you how to hydrolyze it? It's just the reverse of the mechanism that we did. And so when you learn that mechanism, make sure you recognize that you can go forward and then you can go backwards. And that's how we will do deprotection. Maybe we'll look at that in a little more detail later. But I typically encourage the students to learn to write that mechanism in both directions. The same is true here. So again, it's an equilibrium, and we will shift that equilibrium by somehow removing water. We can do that with solid state drying agents or again the Dean-Stark condenser. So let's look at a simple example of this. We might have cyclohexanone. We'll react that with tertiary butylamine with a catalytic quantity of H2SO4. These are commonly done in ethereal solvents or DCM. So DCM or ether, depends on the solubility that we have or we want. So there's the formation of the imine, our T-butylamine here, and we replace the CO double bond with a CN double bond. So in terms of predicting products, remember we want to learn these reactions as predict the products. That's fundamentally different than the mechanism. Okay, I want you to understand the mechanisms and be able to reason with them. But if you have to work through the mechanism, for every reaction that you're learning, it'd be like trying to figure out what 4 times 5 was every time. Well, it would be 5 plus 5 plus 5 plus 5. That's 5, and 5 is 10, and 5 is 15, and 5 is 20. We don't do that. We know that 4 times 5 is 20. Okay? In the same way here, the carbonyl and amine, primary amine, so let me emphasize that, primary amine, that is, there are 2 hydrogens on the nitrogen, then we get imine formation. All right, so let's look at the mechanism for this. And again, for the mechanism, I'm going to use the simplest thing available here, just to save drawing time. That'll be the methyl group. I'm probably not going to put Me in there most of the time. Just assume that's a CH3 at the end of the line, the way we do with all line structures. We're going to react this with an acid catalyst, and we're going to make this amine. All right, so there's our reaction. Remember, we always want to get the reaction in front of us, because again, this is one of the sets of reactions where I often find students making that mistake of not getting the mechanism to the observed product. So always make sure your mechanism produces the observed product. All right, so how are we going to deal with this now? Again, of course, we can protonate the amine. That would be the strongest base, but that would be a reversible process, and it's not productive for our mechanism. So there are lots of these kind of things that are going on that we're not going to explicitly talk about, but I will try and mention them as we go through. And if in my mentioning it, it doesn't make sense to you, you can't write the reaction of the amine and the acid in a reversible manner, then reach out to me for an office hour or Q&A session and we'll look at it. But what will also happen is that we will protonate the carbonyl. This is reversible, and in fact, we would say that the equilibrium lies strongly toward, so these 2 unequal lines here are communicating that the reaction prefers to go in this direction, but we can produce some protonated acetone, the protonated carbonyl. Again, the term for this is an oxonium ion, so it's a positively charged oxygen. With this now, we can bring in our good nucleophile to attack that really strong electrophile. Now, our product in this case is the protonated amine. And here, just like before, we do not do a 4-membered ring transition state. So we're going to bring in an external base, and whatever the counterion for the acid was, could be another amine, could be a water molecule floating around in solution, or a lone pair on the solvent. It's not critical for us at this stage to worry about that. And again, in a reversible process, now, at this point, we're at an intermediate stage, okay? And this is a hemiaminal, like we had a hemiacetal before. I'm going to put my base with my proton on it there. Keep this species overall plus, since we started with a plus. Now, that's a hemiaminal. Again, that's a functional group we're going to find in biomolecules like DNA and RNA, okay? Or at least as an intermediate in the formation of some of them. So what do we need to do now? We need to get that proton over to oxygen, because we need the oxygen, of course, to go away to make the carbon-nitrogen double bond. So again, a reaction that is reversible. We have the lone pairs on oxygen. we can protonate. All right, so we now have our protonated hemiaminal, and again we see there's a good leaving group. That's that water molecule, and we have an internal nucleophilic displacement of our leaving group. That's the way we can think about that. This produces, again, in a reversible process, this is now positively charged. This is an iminium ion. Okay, so that's a protonated imine. All right, do you see where we need to go from here to get to there? We need to lose that. Of course, we have a water molecule with a couple of lone pairs. This water molecule could come back and attack the iminium ion, and we'll go back, right? This is the water molecule that we need to remove to shift the equilibrium by Dean-Stark or some other method. And now what we have left in our mechanism is we need a conjugate base, water, amine, counterion. It doesn't matter what that amine base or that base is for our purposes. And we deprotonate that to produce the imine. Remember, this is called the Schiff's base also by the biochemists. So for instance, this is one of the ways that substrates become covalently bound in the middle of enzyme active sites. Now often it's a non-covalent interaction, but there are many enzymes where you do get a covalent interaction, and that Schiff's base is a reversible covalent interaction, right? Reversible by this mechanism. And so that's a way that we can reversibly and covalently bind a substrate, for instance, to the amine in an amine-containing amino acid, if that was one particular amino acid in our protein sequence, and it could bind that in the enzyme active site. All right, so that's imine formation. This will be 19.8, the first video, and then we'll go now, I'll record a enamine formation. That's what this is clarification for 19.8 imine formation. I realized that some of my drawings had gotten chopped off there, so I've come back and moved them down. So again, we have carbonyl compound, a primary amine under acid catalyzed conditions. We replace the CO double bond with the CN double bond. And this is an imine. Remember, for this one, that's a methyl group there at the end. So it starts out with nucleophilic attack of the lone pair on this oxonium ion that we formed from protonation of the carbonyl group.